Hi friends, here in this session we discuss Morare's theorem, Liouville's theorem and the fundamental theorem of algebra. We know that if a function of a real variable is once differentiable, nothing follows about the existence of derivatives of higher order. But surprisingly, if a function is analytic at a point, its derivatives of all orders exist at that point and are themselves analytic there. First theorem, if a function f is analytic at a given point, then its derivatives of all orders are analytic there too. Proof, we assume that a function f is analytic at a point z0, then there exists a neighborhood mod z minus z0 which is less than epsilon of z0 throughout which f is analytic. Hence, there is a positively oriented circle C0 centered at z0 and with a radius epsilon by 2 such that f is analytic inside and on C0. Hence, f double dash of z is equal to 1 by pi I integral over C0 f of s by s minus z whole cube ds. At each point z interior to C0 and the existence of f double dash of z throughout the neighborhood mod z minus z0 less than epsilon by 2 means that f dash is analytic at z0. One can apply the same argument to the analytic function f dash to conclude that its derivative, that is f double dash, is analytic, etc. This proves the theorem. Next, corollary. If a function, that is fz is equal to uxy plus ivxy is analytic at a point z is equal to x plus iy, then the component functions, that is u and v, have continuous partial derivatives of all orders at that point. Proof is like this. Here given f of z is equal to uxy plus ivxy is analytic at a point z is equal to xy. Then the first order partial derivative of u and v exist and they satisfy Cauchy-Riemann equation. Hence, using that Cauchy-Riemann equation, we can write it as f dash of z is equal to uxxy plus ivxxy. Equation number 1. It gives f dash z is equal to vyxy minus iuyxy. This is by using our Cauchy-Riemann equation. Equation number 2. By virtue of the above theorem, f dash z is also analytic at z and hence continuous at z. Therefore, first order partial derivative of u and v are continuous at z is equal to xy. Now, using 1, we can say f double dash of z. By using 1, we can write f double dash of z is equal to what? uxxxy, that is differentiating twice, plus ivxxxy. Equation number 3. And using Cauchy-Riemann equation again, it gives f double dash of z is equal to, instead of u xx we can write vxy, vxy of xy plus, no, it is minus, it is minus I uxy, here uxy of xy. Equation number 4. Also using 2, we can write f double dash of z is equal to vyx xy minus I uyx xy. That is f double dash of z. By using equation number 2, we can write it as f double dash of z is equal to vyx xy minus I uyx xy. Equation number 5. And using Cauchy-Riemann equation again gives f double dash z is equal to uyy minus I vyy xy. Equation number 6. Again by the previous theorem, f double dash of z is also analytic at z and hence continuous at z is equal to xy. Therefore, equation number 3 to 6 shows that second order partial derivative of u and v are continuous at z is equal to xy. Proceeding similarly, we can prove that u and v have continuous partial derivatives of all orders at that point. The following result can be regarded as converse of Cauchy-Gaussat theorem, that is our Morare's theorem. If a function f is continuous throughout a domain D and if integral over C f z dz is equal to 0 for every closed contour C lying in D, then f is analytic throughout D. That is, theorem says that integral over C f z dz which is equal to 0 for every closed contour C lying in D, then f is analytic throughout D. Proof. By our assumption, integral over C f z dz is equal to 0 for every closed contour C lying in D. Hence, this f has a antiderivative capital F in D. That is, capital F is an anti-analytic function such that f dash of z is equal to f z for all z in D. That is, f dash z is equal to f z for all z in D. This is for all z in D. We know that derivative of analytic function is analytic. Hence, f being the derivative of analytic function f is analytic. Therefore, this completes the proof. Next, we have Liouville's theorem and the fundamental theorem of algebra. We begin with an inequality known as Cauchy's inequality. That is, Cauchy's inequality for fn of z naught. Suppose that a function f is analytic inside and on a positively oriented circle CR centered at z naught and with the radius r. If MR denotes the maximum value of mod fz on CR, then mod fn z naught, it is less than or equal to n factorial into MR by r raised to n, where this n varies from 1, 2, 3, etc. Proof. Here given f is analytic inside and on a positively oriented circle CR. It is centered at Z0 and with radius R. Hence, derivatives of all orders of f set are analytic and Fn of Z0, we can write Fn of Z0 is equal to which is equal to n factorial by 2 pi I integral over CR f set by Z minus Z0 raised to n plus 1 dz, where of course, this n varies from 1, 2, 3 etc. Hence, modulus of Fn of Z0, modulus of Fn of Z0 which is equal to, we can put brackets here, Fn of Z0 is equal to n factorial by 2 pi I, put modulus here, modulus of n factorial by 2 pi I integral over CR f set by Z minus Z0 raised to n plus 1 dz. N is equal to 1, 2, 3 etc. Equation number 1. Since mod Z minus Z0 is equal to R and since MR is the maximum value of mod f of Z on C for all Z in C, we have modulus of f of Z by Z minus Z0 whole raised to n plus 1. It is less than or equal to MR by R raised to n plus 1. Hence, the first equation becomes modulus of Fn of Z0. By substituting this value, we get it is less than or equal to n factorial by 2 pi I into this one MR by R raised to n plus 1. What remains? Integral over C dz. While all the others are constant, we can take outside. Integral over C dz, equation number 2. Also, being the length, that is the circumference of circle, mod Z minus Z0 is equal to R in R, and also integral over C dz is equal to 2 pi R. Therefore, this equation, that is this equation number 2 becomes modulus of Fn of Z0, it is less than or equal to, n factorial by 2 pi I into MR by R raised to n plus 1. So, what is integral over C dz? It is 2 pi R into 2 pi R. So, it becomes, which is equal to, we can cancel this 2 pi and here we have R raised to n plus 1 and here we have R. So, altogether we get it is equal to n factorial by R raised to n into, what remains? Here we have MR. All the other get cancelled. So, it is n factorial by R raised to n into MR, or we can say n factorial MR by R raised to n. Note, when n is equal to 1, the Cauchy inequality becomes, here substitute n is equal to 1, this inequality changes to modulus of f dash of Z0, that is putting n is equal to 1, which is, no, it is less than or equal to, it is inequality, it is less than or equal to MR by R, equation number 3. That is, while n is equal to 1. Next we have Liouville's theorem. If a function f is entire and bounded in the complex plane, then fz is constant throughout the plane. It is a very important theorem. That is, since f is entire, the Cauchy's inequality holds for any choice of z0 and R. The bounded condition tells us that a non-negative constant m exists such that mod fz is less than or equal to m for all z. That is mod f of z less than or equal to m for all z. This is true for every set. Equation number 4. Then MR in the previous result is the maximum value of mod fz on C, and by this equation this maximum value must be less than m. That is, our MR is less than or equal to this m. It follows from Cauchy's inequality that modulus of f dash of z0, it is less than or equal to MR by R. This is actually our equation number 3. MR by R becomes less than or equal to M by R. Since the above inequality is true for arbitrarily large R, we get f dash z0 is equal to 0. Since the choice of z0 was arbitrary, this means that f dash z is equal to 0. It is equal to 0 everywhere in the complex plane. Hence, f is a constant function, and this completes the proof of this theorem. Next, we have the fundamental theorem of algebra. That is, the theorem says that any polynomial, that is p of z is equal to a0 plus a1z plus a2z square plus etc. plus an z raised to n, where of course that an not equal to 0, of degree n, where this n is always greater than or equal to 1, has at least one 0. That is, there exists at least one 0 z0 such that p of z0 is equal to 0. That is the statement of the theorem. That is the fundamental theorem of algebra. The proof is by contradiction method. If possible, suppose that pz not equal to 0 for all z. That is, we are assuming pz not equal to 0 for all z. Then the function, that is fz is equal to 1 by pz, being quotient of two analytic function, that is 1 and pz, is everywhere analytic. That is, fz is an entire function. Our fz, that is 1 by pz, it is an entire function. Now, we show that fz is bounded. To prove this, we first write w is equal to a0 by z raised to n plus a1 by z raised to n minus 1 plus a2 by z raised to n minus 2 plus etc. plus a n minus 1 by z raised to, okay, it is z raised to 1. Equation number 5. So that pz, which is equal to a n plus w into z raised to n, that is pz is a n plus w whole into z raised to n. We then observe that a sufficiently large positive number r can be found such that for all I is equal to 0, 1, 2, etc. up to n minus 1, mod a I by z raised to n minus I, it is less than mod a n by 2n. It is for all z with mod z greater than or equal to r. Equation number 6. Then for all set with mod set greater than or equal to R, we have mod W is equal to modulus of A naught plus z raised to n plus A1 by z raised to n minus 1 plus etc. plus A n minus 1 by z, and this is again less than or equal to, this is actually mod W is equal to, put modulus here, it is equal to A naught by z raised to n plus etc. So, it is less than or equal to modulus of, first term is A naught by z raised to n plus second term is modulus of A1 by z raised to n minus 1 plus etc. up to plus modulus of A n minus 1 by z by generalized triangle inequality, and this is again less than n into, it is n times modulus of A n by 2n. Hence, modulus of W, which is, that is mod W is less than mod A n by 2 for all set with a mod set greater than or equal to R. For all set with a mod set greater than or equal to R. Consequently, when mod set greater than or equal to R, mod set greater than or equal to R, we can write modulus of A n plus W is greater than or equal to modulus of mod A n minus mod W, that is modulus of mod A n minus mod W, which is greater than what? Mod A n, it is greater than mod A n minus mod A n by 2. So, this is what? It is again mod A n by 2. So, this enables us to write modulus of P set. Modulus of P set, it is equal to modulus of A n plus W into modulus of z raised to n. It is greater than or equal to mod A n by 2 into mod z raised to n. That is, this is again greater than or equal to mod A n by 2 into R raised to n. Whenever this mod z greater than or equal to R, then mod f z is equal to 1 by mod p z, which is less than 2 by mod A n into R raised to n, whenever mod z is greater than R. So, f is bounded in the region exterior to the disk mod z less than or equal to R, but f is continuous in the closed and bounded disk mod z less than or equal to R, and hence f is bounded on the closed disk mod z less than or equal to R also. Combining these f is bounded in the complex plane, that is, our f is a bounded entire function. Hence, by Liouville's theorem, f z is a constant. Now, f z is a constant implies its reciprocal, that is, our p z is also a constant, but this is a contradiction to the fact that p z is a non-constant polynomial, as its degree is greater than or equal to 1. Hence, our assumption that p z not equal to 0 for all z is wrong. So, that p z is equal to 0 is 0 for some value of z. Hence, p z has at least one 0 there. This is the proof. The fundamental theorem of algebra also provides the following result, that is, if p z Pz is a polynomial of degree n, where that n is always greater than or equal to 1, then it has n zeros. Not all need be distinct. That is, Pz is a polynomial of degree n. It is a polynomial of degree n, where this n is of course greater than or equal to 1, then there exist complex numbers Z1, Z2, etc., Zn, and C such that Pz is equal to C into Z minus Z1 into Z minus Z2 into etc. Z minus Zn. By fundamental theorem of algebra, we know Pz has a 0, say Z1. Then we can write Pz is equal to Z minus Z1 into Qz, where this Qz, or we can say Q1z, this Q1z is a polynomial of degree n minus 1. If Q1z is constant, the proof is completed. Otherwise, that is, our Q1z is a non-constant polynomial. Hence, again by our fundamental theorem of algebra, this Q1z has a 0, say Z2. Then we can write Pz is equal to Z minus Z1 into Z minus Z2 into Q2z, where this Q2z is a polynomial of degree n minus 2. If this Q2z is a constant, then the proof is completed, or otherwise, that is, this Q2z is a non-constant and we continue the work again. That is, for this Q2z, again by fundamental theorem we can find a 0, like that. Since n is finite, this work terminates at a finite stage and we obtain Pz is equal to P of z is equal to Z minus Z1 into Z minus Z2 etc. into Z minus Zn into Qnz, where this Qnz is a constant, say C. Then P of z is equal to, this Qnz is considered to be a constant, so it becomes C into Z minus Z1 into Z minus Z2 etc. Z minus Zn, and this completes the proof. So, here we discussed Liouville's theorem, Morare's theorem and the fundamental theorem of algebra. Hope you enjoy the session. See you next time. Till then, take care.